to our next speaker, Artūrs Bogdanovs from Riga Technical University. And Artūrs is going to talk about recent advances in hybrid and battery electrical vehicle technologies and its impact in Latvian automotive sector. So we move back to road transport and technology development. So Artūrs, please, the floor is yours.
Thank you very much, Judis. Yeah, we are going to go a bit deeper on the component level of the hybrid and battery electric vehicle technologies and analyze what has happened in the last decade. So I will start with some brief introduction, and then we will look at the recent advances in the three fields, main fields of electric vehicle technology. And these are battery technology, e-motor design, and automotive power electronics. Finally, I will speak about the influence and impact of these developments on the automotive sector and conclude with some outlook and future scope. So the motivation for electric vehicle technology development is, of course, our goal to reduce significantly the greenhouse emissions, which form about a quarter from total emissions in Europe for transport sector and 28.6% in Latvia. The automotive sector brings 72% impact on the total transport emissions in Europe, and in Latvia this number is even 93.6% according to 2020 data. Of course, we need to do something to meet the requirements for EU Green Deal, which was introduced in 2019. And by the end of 2050, we have to get at least 90% emission reduction in transport sector. So this can be done by introducing more electrified drivetrain vehicles or less vehicles in total. And again, there are two approaches how to do that, how to force people to buy more electric vehicles. This is legislation push or customer demand and customer responsibility. To reduce the CO2 emissions, again, we have an option of a fully electrified drivetrain, and then we need to use more renewables for power generation, which is more relevant for battery electric vehicle use. And another way is energy consumption reduction. And here we have two summonds, the weight reduction, which is more relevant for city driving, and the volume reduction and the reduction of frontal area of the vehicle, which will be more relevant for highway driving. There are different types of electric vehicles, and the first important disclaimer that the zero emission vehicle is that vehicle that has released 0 gram of carbon dioxide emissions at the specified test procedure. It doesn't mean that it's zero emission always. It is just at this test circumstances, it's driving just in electric mode. The purely zero emission vehicles can be considered just the battery electric vehicle and fuel cell electric vehicle. The range extended and plug-in hybrid electric vehicles are zero emission under most of the circumstances, but at some points they can use also internal combustion engine as mostly the secondary source. And finally, the hybrid electric vehicle is a classical hybrid electric vehicle, doesn't have an option of battery charging from the main supply, and its primary mover is internal combustion engine, but still the electrified drivetrain helps to run this engine at maximum efficiency and reduce the energy consumption. The main battery electric vehicle components are the charging device, which converts the energy from main supply to the battery level. The battery stores this energy and releases or accepts it under different operating modes. Inverter is used for transforming this DC energy to three-phase AC energy for e-motor. And the e-motor translates it into mechanical energy, which is then transmitted to the wheels by means of transmission. So if we analyze this circuit of electrified drivetrain, we can define the three main areas as subjects of optimization. And these are the energy storage and battery technology, e-motor design and performance, and power electronics. We will start with the energy sources and the different energy storage systems available for electrical vehicles are shown in this graph, where you can see them in terms of their specific energy, which means how much energy can be stored in 1 kilogram of this system. It's similar like how much water can be stored in the bottle. And on the x-axis, you can see the specific power. It means that how fast this energy can be released or accepted by the energy storage of 1 kilogram. And this means how quickly we can get this water out of the bottle. So if we look at the conventional drivetrain involving internal combustion engine with fuel tank, it still has beneficial position in terms of specific energy, but another energy storage systems are also going further and further to reach this goal, and we see that lithium-ion batteries are the closest way to reach this specific energy level. And the lithium-ion battery technology has been developed very rapidly within the last decade. Here we can see this development, how much new chemistries were made available to the market. And now we have multiple options of different materials, which allow increase in both power and energy density and create novel structures for better performance and ion intercalation in one-dimensional, two-dimensional, or even three-dimensional group. So there are also alternatives for toxic materials found, and this means that the battery manufacturing process can be can make less impact on the environment. And the main point is that the battery price also reduced significantly within the last decade. If we look at the e-motor design and the state of the art, what's happening like 10 or more years ago, we had two main options: permanent magnet synchronous machine, which was optimized for low speeds and city driving, let's say, and induction machine or asynchronous drive, which was optimized more for high-speed driving. Currently, the development is strongly gone ahead in the direction of permanent magnet synchronous machine with salient pole design. That means that the permanent magnets are hidden inside the rotor structure. Thus, a more unified permanent magnet flux is achieved, and this machine can achieve high efficiency over wider operating range, especially in this field weakening area. So it has better performance for different operating points. And another alternative is the synchronous reluctance machine. The main motivation is that the rare earth permanent magnet materials are very expensive and can become very expensive in the nearest future. So the rotor design without permanent magnet might be very advantageous. And here you can see the different rotor designs made up within the last years. So we get the cost efficiency at the first time, and also we have optimized thermal behavior and excellent efficiency over wide operating range. But anyway, we have complicated manufacturing and control of the rotor. If we want to have high performance, then the rotor design must be very complicated, unfortunately. And another negative aspect is the low power density in comparison with permanent magnet synchronous machine. So the possible solution to overcome this Problem is to use the permanent magnet assisted synchronous reluctance machine just by placing some small magnets inside this rotor structure and thus enhance the power density. So within the last decade, we have novel design mainly of the rotor of electric motors, better performance over wide operating range for the vehicle, and optimized thermal, mechanical, and electrical stability of the e-motor. Last but not least is the power electronics, which is used in electric vehicles in the three main areas. These are charging devices and battery management systems, the main drive systems with inverter design, and of course auxiliary converters, which are not less important because we need to supply energy for different auxiliary systems of the vehicle. For example, heating, ventilation, air conditioning, power steering, and so forth. And the biggest achievement, the biggest transition that was made within the last decade is a transition from silicon IGBT technology to silicon carbide MOSFET technology, which are now available on the market and bring significant loss reduction, very high efficiencies of the power converters, above 99% for drive systems and 95-97% for charging and auxiliary systems, with compact design, high power density, and fast switching performance. This performance can handle high operating frequencies with even reduced switching losses in comparison with silicon IGBT technology, and provides opportunity for faster, more sophisticated control techniques, low total harmonic distortions, and that's what we can see on the phase current waveforms of this inverter using silicon carbide MOSFET technology with hundreds of kilohertz switching frequency. So another way of improving the power electronics is integration into the drive system. And here I can show you the case study of Volkswagen concern. What they started at 10 years ago was a separately machine and separate converter connected with the wires, and within this decade, they implemented the unified structure with fully integrated converter inside the machine. And this is something that they presented this year on the conference with full novel permanent magnet synchronous machine design with fully integrated power electronics. Another big hope for the nearest future is the higher voltage rated gallium nitride devices, which will be hopefully available on the market soon. They will provide even higher efficiency, faster switching and performance, and even more compact design. And even now, the available on the market devices can overcome the silicon carbide MOSFET technology in terms of switching losses, but the potential for further improvement is still large. And as the result, we see the economical influence first. The battery price for electric vehicles has dropped significantly. If we compare the 2013 with 2020, at least 4 times smaller price for battery pack is now. And of course, the total price of the electric vehicles has reduced also. And this caused that customers are more and more interested in electric vehicles purchase. And this graph shows that the governmental part of the customers is becoming less, and more customers from private sector are demanding the electric vehicles. The environmental influence has not changed dramatically, unfortunately, but still, if we look at the road transportation in Europe, then we reached a peak in 2017, and now there is slow but gradual decrease in total road transportation emissions. And the nearest future, if the vehicle number will grow, we might expect more gradual or more rapid decrease of CO2 emissions in this sector. And of course, the number of electric vehicles is growing both worldwide and in Latvia. The very interesting point is the year 2020, when we see that the most electric vehicles were sold in Europe. And before that, China was always the leader. So this is a very rapid increase. And also, if we look at battery electric vehicle registrations in Latvia, we see almost exponential growth and the tendency. So, of course, economical aspect forced this growth, and we can expect more significant emission reduction in the next decades. Finally, to Outlook, I would like to emphasize that any type of electric vehicle is intended to save energy consumption and reduce emissions. Therefore, each saved gram of carbon dioxide matters, and each technology is good. Most of the influence for this electric vehicle popularity was due to advances in automotive battery technology, e-motor design, and power electronics, but there were also other technological advances not covered in this presentation. So these improvements caused significant price reduction, and electric vehicles are now affordable for a larger customer group, and therefore the number of sold EVs is growing. So we can expect the emission reduction in transport sector very soon and the next future. There are 2 points for the future scope, let's say 2 threads, that due to a rising number of EVs, we will also have rising electrical energy demand. And therefore, more focus must be made on the electricity generation from renewable energy sources. And another aspect is the infrastructure, because further technology improvements with legislation push and customer demand can lead to a sudden boom of electric vehicle demand from the customer side. And this might be a threat for infrastructure that might be not ready for the moment. So it needs to be developed as soon as possible. Thank you very much for your attention, and I will be happy to answer your questions at panel discussion, or later on you can write them on my email.
Yes, thank you, Artūrs, very much for your interesting presentation and to kind of giving the overarching situation where we're at with the technological advancements and real life impact of environment on the cars being used. So, but due to the time limits, we won't take questions in this moment. So thank you, Artūrs. As you mentioned, we're going to talk about, of course, about these matters during the panel session.